Well, we've talked about a lot of matched things in this course so far. We have a matched source and a matched load. We have conjugate match. We're going to add one more value or idea that uses the word matched in its name, and that is the idea of a match component or a match device. So what is a matched component? A match component is a device that is more than one port. We have a match load, match source. Those are one-port devices. Of course, most devices are multi-port devices, two-port devices, or three or four. And we have a concept of a matched component, likewise, for those two or three or four, etc., port devices. The idea of what is a match component is sometimes confusing for students or engineers and misunderstood. So we want to make sure that we understand what we mean by that. In radio engineering, microwave engineering design, almost all of the devices that we will use will be matched devices, matched components. So what is a match component? If we look inside the device itself, it's one whose port impedances are numerically equal to Z0. Now, it's more complicated than that, but we'll start with that as a first approximation there. We have something in the design that tries to ensure that the input impedance of the device or the output impedance of the device is numerically equal to Z0, the characteristic impedance of the transmission line that we're going to use to connect matched components or matched devices to each other. Of course, the benefit of that is if we assemble a design of microwave components where all of those components are quote-unquote matched components, we can connect them together with transmission lines of characteristic impedance Z0, 50 ohms typically, and we find that we will preserve maximum transfer regardless of the transmission line length. And again, that's the beauty of this, is once we make sure that all the components we're using are matched, then we don't really have to worry about the length of the transmission line that we use to interconnect them. So the confusion comes in when we extend the idea of a matched component from simply a one-port device, a match load or a match source, into a multi-port device. So what would a four-port match device or match component, what does that mean if we were to say that? Well, let's say we take our four-port match device here and we connect to all but one of the ports matched loads. Now, these might literally be resistors numerically equal to Z0, or more likely, these are going to be the input impedances of other matched devices. So we've connected a device to port 3, and its input impedance, because it is a matched device, is numerically equal to Z0. But whether these impedances, these matched impedances that we have, Z0, are literally resistors of 50 ohms or the input impedance of some more useful device, it doesn't matter. If we have a four-port match device, what we'll find is this. When we take a four-port component and we connect something to three of the ports, what we've done is create a one-port device. A four-port device with three of the ports terminated in some load, in this case numerically equal to Z0, we have now a one-port network, and that one-port network has an input impedance that describes the entire circuit looking into that port. If that input impedance turns out to be Z0, when all other ports are terminated in loads numerically equal to Z0, then we say that is a matched device, if this is true for any and all of the ports. So in other words, if we were to go through and put a matched device at port 1 at this port, and this one and this one, and then determine the input impedance of this second port, it was Z0. Likewise, if we did the same for the third and the fourth, the input was Z0 for all four ports when attached to other matched devices. If in every case the input impedance is Z0, then we can say that this four-port device is a matched device. Now, we could do the same thing with the source. Perhaps we put a match load here, and then on this port we put a matched source. And of course, that's supplying energy into the device, and so some energy will come out of the device. If this is a matched device, then the source impedance, the equivalent circuit of all of this, will numerically be equal to Z0. So if the input impedance, the port impedance, is Z0 for every port, when is connected to other matched devices, then we consider this four-port device to be a matched device or a matched component. So here's where kind of the confusion comes in when with these matched components. Let's say we have a situation where we connect impedances to these three ports which are not numerically equal to Z0. The question then, what will the input impedance be? Generally speaking, we'll find the input impedance in that case will not be equal to Z0. If we take a matched device and connect it to devices that are not matched, that don't have port impedances of Z0, then we'll find that the port impedance, even of our matched device, will not be equal to Z0. And that's true, generally speaking, for all ports. So in other words, a matched device is not one where the port impedances are always equal to Z0. It's a device or component where the port impedances are equal to Z0 if all other ports are connected to other matched devices. And so to make this whole system work, if we were to go and make a microwave system out of, 6 different microwave components, the only way that we could preserve maximum power transfer, regardless of the length of the transmission line that connects them, is if all 6 of those devices are matched devices. And ultimately, all the ports attached to those devices are terminated in matched loads, impedances numerically equal to Z0. If we have even one device that's not a matched device, or even just one port that's not terminated in a matched load, that enough, theoretically, is enough to completely destroy the maximum power transfer associated that we desire for our system. All of a sudden, the amount of power transfer would be less than the available power, and it would depend explicitly on the lengths of our transmission line. The only way this works is that we put together a system completely of matched components and matched components only. Even one matched component, even taking one port and connecting an impedance to it that's not matched, will destroy then this matched system and essentially reduce the power absorbed by any load or the power delivered by any source from its power that's available. A good way to think about this is, let's say, a length of transmission line. All right, length of transmission line. A length of transmission line is a 2-port device, and it turns out a length of transmission line is a matched device. If we go through and we connect some arbitrary impedance to the end of one end of the transmission line, we find that the input impedance will just be some arbitrary input impedance. It won't be equal to Z0. But we know that if we terminate the transmission line with a load numerically equal to Z0, that's a special case that causes our input impedance at the other end of the line to be equal to Z0. The input impedance is equal to Z0 if the other port, the other end of the transmission line, is connected to a matched load. If it's not connected to a matched load, the input impedance is no longer equal to Z0. And of course, that's true for either port on the transmission line. Same thing for source. If I connect a source to a length of transmission line, it will transform the source to a new source impedance that's very different from the original one. Who knows what it would be? Depends on the length of that transmission line. The exception, of course, is our special case where we connect a matched source to our transmission line, and the transmission line then transforms that matched source into a new source, which likewise is a matched source whose source impedance is likewise equal to Z0. When our source impedance at one end is equal to 0, the source impedance at the other end will be equal to Z0, but only for that situation. And likewise, that's true regardless of the length of the transmission line. So the length of a transmission line is a matched 2-port device. It will present input or output impedances numerically equal to Z0, provided that you connect a device that is likewise matched at the other end. The last thing I'll say that students sometimes mess up or get confused about is a matched device can't change the impedances of the things connected to it. Sometimes students will say, well, gee, if I have a matched device here, it will reach out and somehow change this impedance into a value equal to Z0. And it won't do that either. So again, the key thing that we have in a microwave system is we must use all matched devices, which means that all the devices present impedances numerically equal to Z0, provided that they are attached to other devices with the same property. Again, we call these matched components or matched devices. Matched sources, matched loads, matched components mean multi-ports, and then of course we have a conjugate match that's thrown in there as well. Make sure you understand all those terms. So here's some photos of matched devices. This is a filter, and you can see it has SMA connectors here. Actually, we'll find out later a filter isn't always matched, but at least in the passband of the filter, we'll find it behaves like a matched device. Here's a 3-port device, which is a coupler. Here's a 2-port device. This is an amplifier. And then this is a 3-port device, which is a switch. Notice in all cases we have an SMA connector. An SMA connector is a 50 ohm transmission line characteristic coaxial connector there. So all of these devices were designed specifically to connect to other matched devices. They must be inserted in a matched system to behave the way that they were designed to behave. If you take a microwave filter designed for a 50 ohm system, for example, and you connect other things to it, other than other matched devices at 50 ohms, you will find that the behavior of your filter will be very much different than what you expect. Now, I say if I connect devices that, matched loads here with impedances of Z0, that the input impedances or the output impedances of all of our ports will be exactly equal to 50 ohms. Now, of course, the problem here is with the word exactly. We're talking numerically, how far do we have to go out in zeros before we can say they're exactly 50 ohms? Well, of course, we can't ever get a situation where we're that perfect. The input impedances in these designs are designed such that they will be close to 50 ohms when connected to other matched components, but of course, they're never going to be exactly 50 ohms. How close to perfection do you get in your input impedances for your matched devices is a very important parameter for describing the behavior of the device. It is one of the most important parameters that we look at for devices. How close to the ideal input impedance do we have if we immerse these devices and connect in a matched system such that they are connected by transmission lines of 50 ohms to other matched devices? So if we order some microwave amplifier or some coupler from some microwave component vendor, will they tell us exactly what the input impedance is when connected to other matched devices? Generally they won't. One of the problems there is the input impedance, of course, is a complex number, and so we have to talk about real and imaginary values there. Likewise, it changes as a function of frequency, of course, and so we have to describe, like all microwave components, its behavior across frequency. Instead of talking about input impedance, which is a complex number, typically we like to describe how well our ports are matched, quote unquote, how close they are to Z0, using a real valued measure. And the two most prevalent real valued measures in microwave engineering are return loss and vswr, otherwise known as vswr. So recall that if we have a impedance at the end of a transmission line, which is numerically equal to Z0, the matched load, that condition, gamma L is equal to 0, and the reflected power from that impedance is equal to 0. And this is how we characterize the impedance on most devices, matched devices. We take a transmission line and we measure the incident power flowing toward that port, and then measure or calculate the reflected power. Of course, if the port impedance is exactly equal to Z0, that reflected power will be equal to 0. And so in this case, if we're in a matched system, we want the reflected power to be equal to 0 in order for the maximum power transfer to occur. And again, this is because we're in a matched system. So what we do is take simply the ratio of the reflected power to the incident power. And so if the ratio of reflected to incident is 0.1, we say that we can infer that the 10% of the incident power is thus reflected. If it's 0.5, 50% is reflected. Of course, what we want ideally is 0 to be reflected, and so we ideally want the ratio of reflected to incident power to be equal to 0. And in good devices, it is a very small number. 0.1, 0.01, 0.001, 1% reflected, 10th of 1% reflected, and so forth. And so instead of talking about, strictly speaking, the ratio of the reflected to incident power, we express this with the decibel operator. 10 log 10 of the ratio of reflected power to incident power. Now, because the reflected power to incident power is a number less than 1, we find that 10 log 10 will give us a number which is negative. To rectify that, we multiply the result by -1. And so we get a return loss that is a positive value. Another way to write this is simply 10 log 10 of the magnitude squared of gamma n. This is the reflection coefficient that we see associated with that input impedance. Instead of ZL minus Z0, we would say Zn minus Z0 divided by Zn plus Z0 for the value gamma there. I showed that right there. This is just the input impedance essentially is the load terminating the transmission line going into that port. And so in this case, again, the result is greater than or equal to 0. Now, I've had a lot of students that argue with me about this because they'll say the return loss is negative. It's going to be like minus 10 dB or minus 20 or minus 30. And that is not actually the definition of return loss. Again, the students are arguing that return loss is 10 log 10 without this minus sign there. But the real electrical engineering standard definition for return loss has the minus sign there. So instead of saying minus 10 dB, it's plus 10 dB once we place the minus sign in there. The reason for the argument that it's minus 10 or minus 20 is a measurement on something called a network analyzer, where we're measuring S11, and typically its magnitude squared is referred to in terms of 10 log 10. Since it's less than 1, it gives us a minus 10 or a minus 20 on the network analyzer. But remember, the return loss actually has this minus sign there. So we convert the values from a network analyzer into return loss. We need to multiply by a -1, making it a positive number. Now, there's a mathematical problem with this definition that can cause confusion. So if we say the return loss turns out to be 10 dB, we can show that that means the ratio of reflected to incident power is 0.1. In other words, 10% of the incident power is reflected, and the 90% of the incident power is thus absorbed by the load. We say we lose 10% of the incident power. That's why we call it a return loss. It reflects away and therefore isn't absorbed. So that's for a 10 dB return loss. Now let's go to a 30 dB return loss. 30 dB, that sounds bigger than 10 dB. It's return loss. It sounds like we have more loss. But if we go through and look at the math, 30 dB corresponds to a value of 0.1. 10 log 10 of 0.1 will give us minus 30, and we'll multiply that by -1. That would give us plus 30. So in this case, we have just 1/10 of 1% of the incident power is reflected to the load, and therefore we have 99.9% of the incident power absorbed by the load. That's a better situation than the previous one here. We lose 0.1% of the incident power. A 40 dB return loss, therefore, would correspond to a loss of 0.01% of the power. That would be better, but again, it sounds worse because our loss is numerically larger. What we find is a return loss that has a larger numeric value is actually better. We have less lost energy when our return loss value is larger. In fact, the ideal return loss would be infinity. If we have infinity, then we have no reflected power. 10 log 10 of 0 is minus infinity. We multiply that by minus 1. That gives us plus infinity. The worst return loss we can get is, in fact, a value of 0 dB. When we have a value of 0 dB, that means the magnitude of the input reflection coefficient is 1. The input impedance is purely reactive. All of the incident power is returned and reflected, and none of it is therefore absorbed. So this is counterintuitive when you think about it. Loss sounds bad, and it is bad. We want, we want less loss, not more. If we're talking about losing our money, we want to lose less money, not more money. Losing our mind, we want to, minimize that, of course. What about return loss? It turns out, again, the numeric value of return loss that is larger in decibels is better than the smaller value. But again, that does not mean we have more loss. The larger the number, the less power we've lost due to reflection. So you have to kind of keep that in mind. Students sort of just inherently feel like the larger number should be worse if it describes a loss. But in this case, the larger number is better. So a second real valued measure of the port impedance, how good of match do we have, how close to ideal are the port impedances of our matched device. A second real value parameter is what we call vswr, voltage standing wave ratio, sometimes referred to as vswr. So we look at the total voltage along our transmission line, and we can write it in this form. And I've written here in terms of gamma in. Again, I've used the input impedance since it terminates the transmission line there as opposed to gamma L, but it's the same value. If we look at the magnitude of this total voltage, we would get this result. I've gone through here and multiplied the e to the minus j beta z, well, this whole thing by e to the plus j beta z, and we can rearrange it in this form, and notice there's a 2 right there. This first term then doesn't change with a function of position, but the second one does. And so we see that the magnitude of our total voltage is not a constant with respect to position. And of course we've seen this before, right? The peaks and nulls associated with the total voltage. At some places in the transmission line, we get the largest value of magnitude, and other places the smaller. We can do a little algebra, and we can show that the largest magnitude of voltage we find along our transmission lines, we move up and down our transmission line searching for the peak of our voltage magnitude. Again, this is the point at which the magnitude of the oscillation is the largest. We can show that that magnitude is equal to this, 1 plus the magnitude of gamma in. The smallest magnitude of oscillation we find, where we get the lowest point in the magnitude, we can show is equal to this. And notice it's almost the same as the maximum. The difference is, the value of minus as opposed to plus. Since the magnitude of gamma in is a positive number between 0 and 1, we find this number, 1 plus the magnitude of gamma in, is larger than, of course, this, where we have 1 minus this positive value. Now, we can go and take the ratio of this maximum value to this minimum value, and that ratio is called the voltage standing wave ratio. We insert it in here, and the interesting thing is the magnitude of the wave amplitude, the plus wave amplitude, complex wave amplitude, V0 plus, those constants cancel out. And so we get this result. And what we can see is this really is just a transformation of the magnitude of gamma in into some real value. Now, you might think, gee, this is kind of pointless. Why don't we just talk about the magnitude of gamma in? That's really what we did with return loss, only we, of course, expressed it in decibels. So why do we go through this mathematical procedure, this transformation into VSWR? Well, this is really an historic measurement for determining impedance match. This goes back 100 years, probably, to the early days of radio, to try to figure out how good a match did they have. And what they would do is take a transmission line, usually a coaxial transmission line, and they would sort of open it up and probe with a diode, or not diode, a crystal detector, the magnitude. They would literally measure the magnitude of the voltage up and down a transmission line. And they would plot then the magnitude as it gets larger and smaller, and measured the peak and measured the minimum, literally measured the two values, and then took the ratio, and that was vswr. And of course, what happens if you look at this transformation is when gamma in is equal to 0, which of course is what we want, the vswr is equal to 1. And what that means, of course, is that the maximum magnitude and the minimum magnitude are the same value. In that case, the magnitude of the total voltage is the same everywhere. And that occurs when you have no reflected wave. You just have an incident wave. And of course, that's what we want. We don't want any reflected wave. We only want an incident wave. In that case, the magnitude of the total voltage will be a constant everywhere, and therefore VSWR is going to be equal to 1. The worst case scenario is when we have a magnitude of gamma in which is equal to 1. Again, that would correspond to an input impedance that was purely reactive. All of the incident wave is reflected. And in that case, the VSWR goes to infinity. And so by taking the ratio of the largest magnitude, and again, this is of the oscillation on the transmission line, to the smallest they could find, they would get a value which would tell them how good the match is. Closer to the value 1, the better the match. The larger the value of VSWR, the worse the match. Again, VSWR, this is a very literal description of a measurement that was done in the early days of radio engineering. And again, this is really why it works. This is what they were measuring at that time, a value that depends on the magnitude of gamma in. So this basically just shows mathematically what I spoke about on the previous slide. When we have a perfect match, when the port impedance of our matched device is what it's supposed to be, a value of Z0, then the reflection coefficient is going to be 0, and the VSWR will be equal to 1. Specifically, the max magnitude and the minimum magnitude are the same magnitude, the same value everywhere, simply the magnitude of V0 plus, and that's because there is no minus going wave. The worst case is when the magnitude of, this actually should be gamma in, is equal to 0. In that case, the VSWR is equal to infinity. This is when our impedance, again, is purely reactive. The minimum voltage would be a 0. That would be a null that we'd have, and the maximum would be 2 times the magnitude of V0 plus. This is when the plus and minus wave are they're equal magnitude, and they'd be 180 degrees out of phase. We get a location where the magnitude goes to 0. There'd be other locations where they would be equal magnitude but in phase, and that's why we get twice the magnitude there. So the VSWR is dependent on the magnitude of gamma in, just like the return loss is. The difference here is VSWR, like we said, goes from a minimum value of 1 to a maximum value of infinity. 1 being good, infinity being, of course, the worst situation. So the question is, what is a value of, let's say, the VSWR of 3? Well, 3 is not very far from 1. Certainly 3 is a lot closer to 1 than it is to infinity. We say big VSWR is bad. So does that mean like 10,000 is bad, or 5,000 or 500 is bad? Well, all of those are bad. But even a VSWR of 3 turns out to be not a very good match. And so what we find is VSWR isn't a very sensitive measure. Anything slightly better than, well, between 1 and 2 would be a good match. Anything better than that would certainly not be considered to be a very good match. So 1 and 2, between 1 and 2 is okay. Between 2 and infinity is bad. Return loss has a much more sensitivity because we're using the log value. So, a good match might be a return loss of, let's say 30 or 40 or 50, 60 or more dB, something like that. So Return loss really is the more used parameter with respecting to impedance match. VSWR is used to describe the port impedance, frankly, only when the vendors and their salesmen are trying to hide the fact that their match isn't very good. Again, VSWR doesn't really have much dynamic range in terms of describing a very good match, and so mixer ports are sort of notorious for describing their impedances in terms of VSWR as opposed to return loss. And the reason is because mixer ports typically don't have a very good port impedance. Now, there's reasons for that. It's not that the designers of mixers are, not particularly adept at microwave engineering. There's reasons for that we'll talk about when we get to mixers. But again, if you see a VSWR describing a port impedance, it probably means it's not very good.